Hello everyone, this is Zhifeng Gao from the Food and Resource Economy Department at the University of Florida. I help coordinate the economic component of the SDRI project. Today, Dr. Song's group from the University of Arizona and I are going to present the results related to the economic analysis of the project. The economic cost and benefits of grafting is one of the most important factors affecting the adoption of this technology. The economic working group mainly work on three objectives of the project. The first objective is to develop a customizable decision support tool for growers to evaluate the economic cost and benefit of grafting technology based on their unique situation. The second objective focuses on the decision models and tools that help more cost-effectively produce grafted transplant. And the last objective is to identify the factors affecting grower adoption of grafting and quantify the broader impact of grafting adoption, such as its impact on environment. Let us first talk about the outputs related to the objective one. The success of decision support tool rely on a large amount of field trials to capture a wide range of variations in the performance of grafting associated with crop, location, production system. In the past several years, the Economic Working Group has developed enterprise partial budgets for various crops, mainly using field data from Florida, Washington, and Arizona. In Florida, we have compared the economic cost and benefits of grafted tomatoes and the different plant densities in high tunnel and open field production systems, as well as in fumigated field. In Washington, the economic returns of grafted and non-grafted watermelon has been compared, and in the future, similar analysis will be conducted for tomatoes and eggplants. In Arizona, the cost of using grafted cantaloupe has been evaluated. The take-home message from this analysis is that using grafting increases the production cost, mainly due to the increased cost of transplant. The cost of grafted transplant on average are about 2 or 3 times higher than that of non-grafted transplant. However, using grafting most time will result in higher yield, which means grafting can generate more revenue for growers. The additional revenue associated with the increased yield of grafted crops in most cases can offset the additional cost of grafted transplants. As a result, grafting in general can result in a higher net income based on the field trial in the current project. We also notice that the economic performance of grafted crop depends on the rootstock production condition, such as whether it is open field or high tunnel, plant density, and so on. Grafted crop can generate about 30 to 80% more net income than the non-grafted crops. However, in few cases, we also notice that grafted crops are less profitable than non-grafted crops. The key output of the first objective of the Economic Working Group is the online economic decision support tool. This tool is developed based on the original Excel VBA-based decision support tool of 2015. The link of the tool is grafted2.ifrs.ufl.edu. The tool makes use of the published research that compares the yield of grafted and non-grafted crops. It is flexible enough to allow users to customize the conditions that best match their need for information. Other than basic partial budget analysis, the tool also allows advanced analysis such as sensitivity analysis and break-even analysis. Let us talk more details of the decision support tool. This is the main page of the website. The user can choose their roles as vegetable producer, researcher, or extension agent. For instance, a grower is more likely to choose the role of vegetable producer. If she clicks the vegetable producer picture, a login page will display. If a user already has an account, she can input the email and password to log in. The benefit of having an account is that she can access all the analyses that she has conducted previously. If a user does not have an account, she can create a new account by simply clicking the button of Create an Account. The user can also simply continue as a guest if she does not want to have an account in the system. After login, the first thing for a new user is to check the user menu that is available in both PDF and HTML format. If a user is familiar with enterprise budget, she can click Start New Analysis to use the tool. This page asks users to input some information so that the studies that best match their need will be extracted from the database of the tool. For instance, she can select the state where the farm is located. The most important input is the crop name. The user can select tomato, watermelon, cucumber, and other popular crops for which grafting is widely used. The user can also specify the scion and rootstock of their interests. Other customizations that the user can do include crop type, which specifies whether the crop is grown using organic or conventional method. Production system specifies whether the crop is grown in open field, high tunnel, or greenhouse. Production season specifies the growing season of the crop. After the user clicks the search button, the studies that match the user's specification will be displayed. If there are no studies that exactly match the specification, studies that are more close to the user's inputs will be displayed. The user can click Submit to go to the next page. On the next page, the user can select the studies that they are interested by using the check mark on the right hand of the web page. Then they can click the Submit. The next page asks the user to specify the farm size. The default farm size is 1 acre. If the user are only interested in the economic cost and benefit of grafting per acre, she can simply click Analyze button. Then the economic cost and benefit of grafted and non-grafted crops will be displayed. The first figure displays the net income, which is the difference between revenue and cost. Second figure on the page displays the revenue. For instance, this figure shows that the revenue of grafted tomato is much higher than that of non-grafted tomatoes. The third figure displays the partial cost at the different production stages. It mainly classifies the production stages into pre-planting stage, production stage, and harvest stage. We can see that the cost of grafted tomato is higher than that of non-grafted at the pre-planting and harvesting stage, but the costs at the production stage are the same because we assume that the growers use the same production management strategies for both grafted and non-grafted tomatoes. The strength of the tool is that the user can change the quantity and the price of all the inputs and outputs based on their own situation. This can be done by clicking the Customize Budget Sheet button at the bottom left of the page. The user can also navigate different analyses using the panels on the left side of the web page. The panel includes detailed budget sheet, the comparison analysis that we just discussed, more advanced analysis including sensitivity and break-even analysis. Because of the limitation on time, we don't discuss these functions in details today. At this point, we also have a survey to collect user response to the grafting tool. We sincerely hope you can take our survey and give your opinions. Next, Dr. Sang's group will present the results related to the second objective of the economic working group. We don't discuss the content related to the third economic objective because the activities are still going on. Thank you.
Hello, my name is Youngjun Son at the University of Arizona. Other project members are Dr. Kubota at Ohio State University, Dr. Tronstedt at University of Arizona, and here are our current and former PhD and master students who participate in this project. In our first work, we developed a simulation-based optimization tool that was used to obtain optimum labor allocations for a given grafting facility. So we compared its performance against the performance of human experts. And based on the results that we have obtained, we were able to reduce the labor cost by using our proposed algorithm. Next slide shows more detail. For inline layout as well as cellular layout of a grafting facility, the time per plant in minute using our proposed algorithm, we were able to reduce the time compared with solution provided by an expert plant scientist as well as expert facility grafting facility manager for time as well as cost. The same result for cellular layout in terms of the time and the cost. In our next work, we were able to develop a machine learning algorithm that automatically detect micro level motions of hand gestures that are involved in grafting processes, given the data that is coming from virtual gloves that are worn by grafting operators. So for example, here is the task that are detected by our machine learning algorithms, such as joining, clipping, cutting, and a rootstock cutting. And here is the time that was calculated by our algorithms. And the next column is the acceptable ranges that has been developed based on historical data. And when a certain operator is performing these operations, when we calculate this processing time, if it belongs to the regular ranges, which is fine. However, if a time is smaller or larger than the regular ranges, our algorithm automatically detects and notify abnormality to the plant manager and so on. So extending our work, the data that are collected by our virtual glove, we are putting that into virtual reality setting so that that can be used to train novice operator based on the movement of an expert operator.
Hi everyone, in this part of the presentation I will talk about the radio frequency identification and ultra-wideband based localization tracking framework that we are using for material flow and workflow analysis. So we are using RFID for micro and macro level motion study of the material flow, and we have used dynamic k-nearest neighborhood and hidden Markov model based localization and tracking respectively. So this system consists of three different units: the real system, which is mainly hardware related to RFID, and the localization units, which requires for locating the object using the dynamic k-nearest neighborhood algorithm, and the tracking unit, which track the object using the hidden Markov model. So as you see here, our framework achieved a really good localization accuracy in terms of the localization error. The error is very small, like 0.36 meter. And as a matter of fact, this work is already accepted for publication at International Journal of Sensor Networks. And next, we have extended our localization work to the tracking work, which basically use the dynamic k-nearest neighborhood algorithm as a basis for tracking the object. And we have conducted multiple experiments using different patterns of movement and different speed. So as you see here, in terms of the average tracking error, we have achieved the tracking error as low as 0.4 meter. So this work is under working paper at this moment. However, sometimes we require more accurate localization and tracking to do the workflow analysis. Therefore, we have used a new technology called ultra-wideband for the workflow analysis. This ultra-wideband tags can detect, track the object within accuracy of 10 centimeter. So after doing some experiment at the grafting facility, so we have come out with a Gantt chart which shows the processing time of different trays and for different workers. And for our framework, the average accuracy for the worker labeling and the processing time calculation is very high. And this is also under working paper at this moment. Next, we are working on the data-driven irrigation monitoring. So this work is mostly related to minimize the worker traveling time in seedling propagation facilities. So basically, it aggregates different irrigation monitoring requests in a single trip so that the worker can perform this irrigation very quickly. And after implementing this framework, so we have for different scenarios, the reduction in travel distance is more than 50%. And this one is also under a working paper, which will be submitted very soon. Thank you.
Okay, so the next topic is about Grandes. So Grandes is a web-based grafting nursery decision support system, and then it can estimate OPEX and CAPEX based on production scenarios. So it takes multiple different types of input variables and then also information such as crop type, which species of grafted plants they are trying to produce, year-round weekly production schedule, how many plants of that particular week the propagator or production manager is planning to produce. Propagation cycle, how many days in seeding stage, how many days in grafting, how many days in heating, and all that cycle-specific information. And then it has a unique option of including storage of seedlings so that they can distribute the labor input for the grafting. Location, facility type, automation, those are also important input information that would determine heating, cooling requirement, as well as the labor requirement, and then also the capital expense. And then labor wage information, utility rate, types of material, and unit price. So all these details are also you can either input by yourself or use the default value. So output includes all these input variables for the user's record, multiple tables of information, and then also schedule, production schedule, how many plants to produce, how many trays of plants produced per week. If optional optimization was selected, the system can optimize the schedule for you also. And then most importantly, cost information at the end.
In our next work, we integrated discrete event simulation that represent manual grafting module, semi-automated grafting module, fully automated grafting module. By combining this simulation with analytic hierarchy process, we were able to develop a decision support system which can give the optimum layout design. For example, given manual, semi-automated, fully automated grafting, what is the optimum considering time, cost, as well as resource utilization. So if you are interested, please refer to this published paper. Thank you.
Hello, my name is Russ Tronstead. I'm with the University of Arizona, and I'd like to share with you some break-even cost estimates that we obtained here in a study looking at the difference here in terms of break-even production costs from grafted, non-grafted, and direct seeded cantaloupes here. The study here was done more than 10 years ago in regards to the actual physical trials that were done, and they were conducted in 2007 and 2008 in the fall, and in the spring of 2009 and 2010. And you may wonder why we want to bring this to light now, but in part at the time, the producer cooperator did not want us to share these break-even cost estimates because they felt that that would really put them at a comparative disadvantage to the entities that were buying their cantaloupes from them. They thought they would be bidding down the prices there for them. In looking at the differences here, one of the biggest differences here was just the cost of the transplants and looking at the grafted versus the non-grafted. 60 cents per pound is what we imputed for the grafted transplants versus 6 cents for the non-grafted. That 54 cents per pound may not seem like much, but when we had 5,600 plants per acre, that amounts to $3,024 per acre difference there. So that higher production cost has to be made up for in terms of more yields or even a better marketable fruit or higher price fruit. So we also looked at the fruit size there in terms of looking at these differences here. And in terms of these break-even prices, we used most of the cost estimates from figures that were obtained from the Arizona specialty crop budgets there. And we had differences then just in relation to some of the practices that were differences. But for the most part, these were side by side and even down in the same row there. Advantages and disadvantages there. With regards to looking at the size by harvest, this shows the daily harvest here. And so every day the workers were picking and they were keeping track of the size of the fruit that was coming off of the different plots here. This example here just shows that size 9 was the most common here. The next most common was size 12. And size 12 was what we used as the base for this study here. So all of the cost estimates are in relation to the size 12 fruit. When we look at this figure here with regards to the break-even cost estimates by year and the different production methods here of non-grafted, grafted, and direct seeded, you can see direct seeded came out on top every year here by having the lowest mean overall of all the different trials out there and replications. So you can see that it was only in 2009 that there was kind of a yield bump for grafting that put it in contention to where it would rival the lower cost estimates here for the direct seeded or even on the non-grafted. And we think that part of that was due to just the level of the pathogenic pests that were present there, that we didn't have that much in terms of Fusarium wilt or root knot nematodes present there. And of course, if you don't have those present, grafting's not going to necessarily be profitable. Hopefully this information has been helpful to you, and thank you for your attention here.